So let's now consider the topic of general linear transforms. So we're going to start by looking at this expression here, which generalizes the discrete Fourier transform and maps an image, here's our image here, into transform space. So these are transform coefficients by this operation here. So the operation contains a pair of summation functions, but these summation functions are simply running over all the rows and all the columns in the image. And for every pixel, what we do is we multiply the intensity of that pixel. So fmn is going to be an intensity or luminance image. We multiply that by another four-dimensional function, which is kind of mind-blowing, but you can break this down, such that if you imagine you were to fix k and l, then this function, so if we fix k and l, then this b as a function of k, l, m, and n will only vary over m and n. So fix k and l values, whatever you want them to be. This summation is only operating over the m and the n values, which effectively are matching the pixel values. So the way to think about this is that here's your image you want to transform. For a given k and l, you have this other image because it varies as a function of m and n. So for a given kl, you have this other image that you place on top of the image you want to transform, and then you're multiplying the pixel values in your image with the pixel values in what we will call a basis image, which is a slight corruption of terminology, but let's just use it for the time being, and sum. Okay, and that gives you one value for that particular k and l. As we vary k and l, we then produce a different scalar result in this computation. But what we're doing is the same. We're basically taking, in this case, another image, which we call the basis image. So it's going to be different from the first one we've chosen. Take another basis image, and we repeat this multiplication of image luminance values with the basis image values for that particular KL sum, and that gives us another value for as a result of this calculation. So as we vary k and l, we basically fill up transform space, and so transform space becomes complete when we run through all the little k's and little l's up to a number that typically is equal to the number of that will be equal to the number of basis images, which usually, if we look at the next slide, usually k is equal to the number of rows in the image and l is equal to the number of columns, but that is not always guaranteed. So it might be that we have a larger number of k or basis images as indicated by large k and large l, but typically the transforms that you'll meet will have the property that k is equal to large k is equal to large m and large L is equal to large n. So if we take the BKLMN and think of, if you hide the K and L, this is just a function of M and N, so it's like an image. And if you allow the K and L to vary over all their possible values, 0 up to K minus 1, 0 up to L minus 1 in this example, then that complete set of BKL as a function of spatial position is known as a basis set. And these things here are known as the transform coefficients. So when you collect the transform coefficients over all little k values and all little l values, then you have a complete transform space. So for the particular case of the discrete Fourier transform, well, the first thing is that all general linear transforms, and in fact most transforms that you're going to meet, fit into the category of general linear transforms. The thing that differs them is that the basis images are different. So, for example, for if we say we want to take our image into the discrete Fourier domain, then that dictates the basis images that we use for that process. So the basis images define the transform, and this operation is the same for all of the general linear transforms. Okay, so here, for example, are the basis images that correspond to the two-dimensional discrete Fourier transform. So the top left, this top left image, it contains all ones, because this corresponds to a cosine wave as a function of space, which has zero frequency in both of the two principal directions. The two principal directions are the directions of the increasing column number or increasing row number. So here we've got no rate of change. It's just a cosine of 0, so it's a constant value of 1. On this side, this looks the same, but it's not, because here what we've actually got is a sine of 0, so 0 frequency. So this is all zeros. It's just the scaling of the I think I've said MATLAB here, but I might have used Python to do this. I can't remember. So so this is actually all zero. So it's difficult to tell this from this because of the auto scaling. But you can generate these yourself in the practical and see what the DFT looks like, and we'll talk about how to do that a bit later on in this lecture. So if you compare this and this, for example, so look at this and look at this, you can see that this is so this is a little oscillation. It's going from +1 to 0 to -1 to 0, and this is going 0 to +1 to 0 to -1. So these two are similar, but they're an oscillation, but there's a phase shift between them. And we can also see an oscillation here that's the same rate as this one, but it's moving in a different direction. And here you can also see a phase shifted version of that one. As we move through the basis images that move more in this direction and more from this direction to this direction, we're getting to faster frequencies. Here we're just hitting the sine wave wherever it's either 0 or 1 or -1, so it's difficult to say. You'd have to go through and see what the values are in this array to make sure that you were interpreting this correctly. So yeah, these are the basis images for the discrete Fourier transform. So basically you have oscillating cosines and sines that, and the key thing is that what the discrete Fourier transform is doing is that it's giving you a set of, if you apply these basis images to an image you wish to analyze, what the discrete Fourier transform is telling you is it's kind of like this. It's taking these basis images as ingredients. It's telling you how to weight these different ingredients and blend them together to reconstruct your original image. Hence, you have a forward and an inverse transform process. Okay, so let's come back to this equation here. So this is a bit messy because we've got two summation signs here. There's another way we can represent this. So note that we are summing over m and n, so m and n disappears once we've done that, and we just are left with little v as a function of little k and little l. So we can also introduce the idea of the matrix inner product, which is just, it's like a dot product between two matrices. It's not a matrix multiplication. The best way to explain this I'll come to in a second. But you can using this notation, you can kind of get rid of those summation signs. If you take this between two-dimensional arrays, large F and large G, as by definition being the sum over the same indices, the sum of the product of the matrix elements over all matrix elements, which gives you one value. And the only other thing that you need to do if you want to use this notation is to include a complex conjugate in case the elements of G are complex valued. So that's a standard definition for a dot product, except for complex valued vectors, except we're treating them as two-dimensional arrays. Now, this needs a little bit of just disambiguation. So when I have, so let's just take an example here. So if I have A, B, C, D, and I want to multiply that by another 2D matrix E, F, G, H, okay, the standard matrix algebra would be to do the usual thing. It's that times that plus that times that. So, and then you basically move along in that kind of pattern. And we're going to say this is by, let's go through it first. So A by E plus B by G will be your first element. Your second element is A by F plus B by H. The element down here will be CE plus DG. I made this matrix too big, but anyway. And this element down here is CF plus DH. Okay, so this is by standard matrix algebra. Okay, so just remind yourself of that when you want to multiply two matrices together. What we're doing here is not that. What we're doing instead is creating an operation between two arrays which collapses us down to one scalar value. And so what we are doing instead is so we're not doing this. So this is standard matrix algebra. So now let's look at the matrix in a product. So we have, let's use the same two, A, B, C, D, and if we do this, let's put a comma there, ignore that dot, and we have C, D, oh sorry, what was it? It was E, yeah, F, G, H, right? E, F, G, H, I think that's what I used. So E, F, G, H, so that in a product, matrix in a product, gives us a scalar value, and that scalar value is going to be AE plus BF plus CG plus DH. Okay, and that's a scalar value. In other words, just one value, right? Not a matrix. So that's what you get when you do matrix in a product. So what is the, as I said, this is not standard matrix algebra. It's I'll explain why we do this. But if you want to write this down using standard matrix algebra, what you would do is you unravel both of these into vectors. So you do this. So you can write this as A, B, C, D. That's your first vector, and you leave it as a row vector. And the second vector becomes a column vector, and that's going to be E, F, G, H. Okay, and when you, if you do a row vector by column vector, so this is 1 by 4, a 1 by 4 vector multiplied by a 4 by 1 vector. So the inner dimensions match. So 1 by 4 by 4 by 1 gives me a 1 by 1. So I get this. I get exactly this. AE plus BF plus CG plus DH. So why do we not just do this? The reason is that when we unravel these two-dimensional arrays, which of course are actually, they start off as images, we lose a little bit the spatial intuition, or the intuition about how the basis image, what the basis image is doing over space. Because when we just unravel the 2D image into a vector, things that were near apart in space become further apart in the vector. That's just a housekeeping thing, but that's why it's useful to introduce this idea of the matrix inner product. So there's also so another way to do this, let's say in a sort of matrix, a recognized syntax for matrices, is to describe this as the sum of the elements of the Hadamard product between matrices. Matrices. Okay, so that's another way to describe this. Okay, so that concludes what I wanted to say about this. So once we have defined this matrix inner product, which collapses many values, a pair of matrices each containing n by m values, onto one value, with this definition you can then rewrite the general linear transform of equation 16, which is the one back here. Just to remind you, it's this one here, equation 16. You can rewrite that in this form. Okay, so the little b, which has which were the subscripts, or taking the arguments k, l, m, and n, you now just represent as with k and l. So you've got a different matrix for each pair of values k and l. Equation 16 now becomes this, and because we included the complex conjugate in the definition, then just get rid of that so you can see the complex conjugate. Then the forward transform of an image can be defined as a set of inner products, of matrix inner products, between the image we wish to analyze, f, and the basis set, or the complex conjugate of the basis set. Okay, so BKL denotes K by L different basis images. So I should say KL different basis images, each of the same size as the image, because you have to have a matching pixel in each basis image for each pixel you have in the image you want to analyze. So that constrains the basis images in some way. And so one of the key things about the definition of these B's is, first of all, you need to know what sort of transform you want to do. So if you want to do a discrete Fourier transform, then that dictates that you're using one type of basis image. Excuse me. But the other thing that's important is that the size of that basis image has to match the size of your input image. And so the definition of the basis image depends on the size of the image you wish to analyze. So these are the two dependencies of that basis image. Now, what we're going to do next is to look at this example here, and we're going to effectively do the calculation to assuming that we have this as our image, a little 2x2 image. Excuse me. And we have, so given that we have this as our image, we have 4 basis images. So we have 4 pixels here. And like I said, the large K and large L are usually equal to large M and large N. So in this case, large M, the number of rows is 2. So large K will also be 2, or large K is 2. It doesn't have to be, but that's a very common situation. And so little k will take values 0 and 1. Similarly, the number of rows here, the number of columns is 2. So first column, second column. So the number of values of L, large L, will also be equal to 2. And therefore little l takes values of 0 and 1. So together we will range k, little k, between 0 and 1, and little l between 0 and 1. So you have B00, B01, B10, and B11 as being your basis images. These basis images in this case are not don't have imaginary parts, so they're purely real, so we don't need to worry about the complex conjugate. If we now take the matrix and a product between F and each of these basis images in turn, we will get the little VLs. So to get little v00, so let's just write that down. So little v00 will be equal to this thing, F times B00, okay, as a matrix and a product, which is going to be equal to, so you just multiply the values together, corresponding pixels together, and sum. So 1 plus 2 plus 3 plus 4, which is 3 and 3, 6, and this is 10. And then we have a factor of 1/2 here. So we're going to get 5 for V00. Okay. Little v01 will be equal to, so 1 by 1 plus 2 by 1, 2 by minus 1, so that's minus 2, so you on minus 1, plus 3, minus 1 plus 3 is 2, and then minus 4, which is minus 2, and then divided by 2 is minus 1, okay, etc. And if you, so you should work through that, so you embed the mechanics of this calculation into your DNA, and then what you will end up with is V being, so this is, so just to be clear, to connect this, there's little v00, which is 5, and there's the value of little v00, which is 5. Little v01 is minus 1, and if you run through the calculations, you see little v 1, 0 is minus 2, and little v11 is 0. Okay, so first thing to note here is that let's look at a few. So I'm not going to say where these this definition of the basis images comes from. Deliberately, you're going to see some hints as to where these basis images come from. But we are going to use this because it helps us get some intuition about what these values are telling us about the image. Okay, so the first thing to note is that most of these basis images have positive and negative values in them, except for this one, which only has positive values. So when we apply a basis image that only has positive values, and those positive values are all the same in the basis image, then what we are doing is we are adding up all the pixel intensities in the image. And then perhaps if we have like a scaling, as in this case of 1/2 for those values of 1, so this is 0.5, 0.5, 0.5, 0.5, what we're doing is we're actually giving the weighting, so we have we're scaling that summation by a constant. But irrespective of whether we're scaling or not, effectively this coefficient in transform space, because of the nature of this basis image that's associated with this coefficient, and only this coefficient, then we're getting a measure of the sum of intensities, and also you can relate that to the average intensity of pixels in the image. So this is our little image F. It has an average intensity, according to this, scaled of 5. The scaling for that average intensity comes from the factor of of the 1/2, plus the fact that we've got, so a real average would add these pixels up and divide by 4. We're adding these pixels up and dividing by just 2. So the average intensity in here is going to be 5 divided by 2, which is 2.5, and you can check that. So 1 plus 2 plus 3 plus 4 is, well, as we said, it's 10. So 10 divided by 4 pixels would be 2.5. Okay, so that's easy, trivial, right? So that's just telling us, giving us some information about the intensities in the image, which is a trivial piece of information, which is the average intensity, but it's a scaled version of that average intensity. Nevertheless, if we take the same transform and we use it to analyze lots and lots of different images, so lots and lots of different f's, then by looking at transform space and that coefficient, we automatically get an idea of what the average intensity is in across each image individually. So the other thing that you will note is that so this is another sort of okay. So the other thing that you will note here is that this basis image, if we were to think of this as a spatial structure, it's basically looking at it's weighting the pair of pixels that lie in a column with a +1, and a pair of pixels that lie in a neighboring column with a -1. So when we have large values for the coefficient associated with this basis image, it's giving us some information about a change in intensity as we move from left to right or right to left. So basically along the rows. This basis image, on the other hand, is weighting rows positively here and negatively here. So it's telling us about, if we get big values in transform space associated with this basis image, it's giving us some information about a change between rows in the image. And so it's telling us about a change in intensity in going from top to bottom, or vice versa, depending on the sign of this change. And finally, this image you could sort of think of as doing something kind of weird and diagonal. So it's telling us whether there's a change as we move in one direction that's different, one diagonal direction that's different from the other diagonal direction. So it's picking up stuff about the diagonal structures in the image by its design. The other thing you notice here is that, and this is very typical of good transform spaces, that if you have a look at this, so you've got non-zero values in 3 of these elements and a 0 value in the 4th element. In fact, it's a weird thing, but a general feature of transforms like this, and I'll show you where the properties come from. A general feature of transforms like this is that they tend to sparsify the representation of the image. So in other words, here we've got no 0 values distributed across the image array, and here we've already got a little bit of concentration of the non-zero values into a subset of the array. As we get to bigger images with more basis images, that's a property that tends to increase. But one thing I said is that, I haven't said anything more about, when we talked about the discrete Fourier transform, we said there was a way to go forward and backward. And here, there's also a way to go forward and backward. And quite amazingly, if you take the process we did here, which is finding the matrix inner product between this image and each of these 4 basis images in turn, you get to this. If you do the same process, so you now take capital V, and you find the matrix inner product between this thing and each of these basis images in turn, you will amazingly get back to F. Okay, so that's a property of this specific choice of basis images. So where does that property come from? So we will see a bit later on some other hints about where this comes from, but this matrix or this transform is easily invertible. It's invertible by basically doing the same thing backwards, because each of these basis images is orthogonal to every other basis image. So you can check that. So to find whether the basis image is orthogonal to another one, you find the matrix inner product between each pair of basis images. Okay, so if I take B00 with B01, for example, and I do a matrix inner product, I get 1 by 1 plus 1 by -1, so I get 0 there, plus 1 by 1 plus 1 by minus 1, so I get 0, right? And the same thing happens with any other pair of basis images. If you take the inner product between the basis image and itself, you also find that they all give you the same result. And so if I take the inner product between B00 and itself, I get 1 plus 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 1. So I get 4, but then I have to remember that there's a factor of 1/2 between each of those basis images, and so I get a value of 1. And a way of thinking about this is if you unravel this basis image into a 4 by 1 vector, the length of that 4 by 1 vector in 4-dimensional space is 1. And so not only are these basis images all orthogonal to each other, but they all have the same length. So each of these has exactly the same length in 4-dimensional space. And because of that, we refer to this as an orthonormal basis set. So form an orthonormal, so that's like orthogonal, except when the vectors are also unit length, you call it orthonormal. And any basis set that's orthonormal is automatically its own inverse, with the one exception that you may need to do a complex conjugate somewhere, but they're basically easily invertible.